So we're going to start talking about Chapter 4, and Chapter 4 is on integration. At the beginning of the course, talked about the two big approaches to calculus that we're going to talk about was differentiation that comes from the tangent line problem, and integration that comes from the area problem. Not going to hit the area problem yet, but we're going to kind of build on what we've been doing with differentiation to get into something that we're going to call the antiderivative to get us into integration in section 1. So our lesson objectives are we're going to be able to write a general solution to a differential equation. We're going to find out what we mean by a differential equation, definitely, and use an indefinite integration notation for antiderivatives. Yeah, that's a mouthful. We're going to get some basic integration rules to help us find these. Yeah, we're not going to start off yet with limits. I'm sure we can find limits in here eventually. Not in this section. And find a particular solution as opposed to the general solution that we talked about up here. So let's first define what do we mean by an antiderivative. And again, you look at let's break apart the word. Anti pretty means the opposite of, undoing. So the antiderivative is something that undoes a derivative. So we say if f, capital F, we use for the antiderivative of this function f, small lowercase f. Oh, getting back ahead of myself. That's if the derivative of the antiderivative is the function. So the derivative of capital F is lowercase f for all x in my interval. That's what we mean by an antiderivative. Again, kind of undoes what we're going on. So here's our example. If my function is 3x squared, then x to the third is an antiderivative. Because if we take the derivative of x to the third, we're going to get 3x to the second. So f of x is the derivative of the antiderivative. Now you notice here we said is an antiderivative. It's one possible antiderivative because of this idea, if you take the derivative of a constant, you get 0. So I could put any constant I want on the end of here. Plus 5, minus 25. Anything I put on here, if I put a constant, add or subtract it, then when I take the derivative, it disappears, and I will get the same function, x cubed. So that's one of the things we got to worry about, is when we find an antiderivative, there are an infinite number of them. There's not just one. So we write it this way. We say if f is an antiderivative on the interval, then we come along with g, and g of x is f of x plus some constant c. We can add a constant to any constant I want to here, and I will get another antiderivative. So this is probably your biggest stumbling block. Well, maybe not, but this is the most annoying one. Whenever you're finding an antiderivative, you need to have that c on the end. So this is some definition, some notation here. So if we're going to start with this example, the derivative of x squared plus 3x is 2x minus 3. Then we say we'll talk about the antiderivatives. We talk about a family of antiderivatives, because those are all of the antiderivatives are going to be this x squared plus 3x plus some constant. C we call the constant of integration. G is the general antiderivative. Then this x squared plus 3x plus c is what we call the general solution of the differential equation. And the differential equation is basically an equation that involves x, y, and the derivative of y. So if you have an equation that includes dy dx in it, or y prime in it, and you're trying to solve it, we're talking about a differential equation because it has a derivative in it. So, for example, this is a differential equation. Y prime equals 6. We can say y equals 6x is an antiderivative of 6 because the derivative of 6x equals 6. So the general solution to this differential equation where the derivative equals 6 is going to be 6x plus 3c. Now here's this notation that we use. And we'll start with the derivative, dy dx equals f of x. We're going to use that differential form that we talked about at the end of chapter 3. dy equals f of x dx. And then we come along with this funky kind of elongated s type of thing. This is what we call the integral sign. It is the symbol we use to represent this idea of integration. So we would say y equals the integral of f of x dx. And so dx here, this is our integral of differentiation, of integration, because we're finding the derivative with respect to dx, so we're finding, or with respect to x, so we're finding the integral with respect to x. Again, we're going to have that dx in there to tell us what's the variable we're considering, we're dealing with. We call this the integrand, and then we get an antiderivative plus the constant of integration. And don't forget the constant of integration. So this is what these integration problems will look like. This is the integration symbol. This is how we say we're doing integration. So these are, again, we get to this idea, it's the antiderivative because they're inverse operations. The integral of the derivative cancel out. So if I take the integral of f prime of x, I get f of x plus my constant. If I take the derivative of the integral, they cancel out and I get my function. You notice on this side I don't get my plus c because my last thing I'm doing is the derivative, and that's going to cancel out any constants that are in part of the integral. But here I'm ending with an integration, so I'm going to end up with a c. I'm getting a general antiderivative. Now, one cool thing that we're going to start off with is I'm going to start you with your shortcuts. So in your textbook, you can go to page 250, or if you have the slideshow, you can click on that. I'll bring up that page here. There's more. There's also the trig functions down here. We're going to be working mainly with these basic formulas here. But like you say, the derivative of a constant is 0, so the integral of 0 is a constant. Now, derivative of kx is just k, so the integral of k dx is kx plus c. Now, I just want to point out these two here. Notice the constant multiple and these sum and difference formulas. For derivatives, we can break these up. Work for integration as well. It's the inverse operation, so it makes sense that some of this is also going to work for us. So we can pull out a constant. It's a constant multiple I can pull out in front and then do the integration. If I have the integral of a sum, it's the sum of the integrals. So that's kind of nice. And then here's the power rule we have. That when we find the derivative, we drop down one power. So when we take the integral, we bop up a power. And then we have to divide by the new power. Here we're multiplying by the previous power. Here we're dividing by the new power. because then when you take x plus 1 times this, the x plus 1's cancel, and you will, or sorry, the n plus 1's cancel, and you'll be left with x to your power. So those are kind of our basic rules we're going to start working with and exploring. Again, we also have the trig ones down here. Those will be helpful for you. So, take a minute and give these a try. So pause the video, see what you think, then come back and I'll do these for you. So for here, and I'm going to break these really down to the basic elements as we're starting to go through here to get the hang of it. When you get more comfortable with this, you will probably shorten this up a little bit. But I'm going to go through step by step here. I'm going to first use the constant multiple rule and say this is 3 times the integral of x dx. And then I can look to my sheet and say the integral of x is just going to be x to the second over 2, because this is x to the first, plus a constant. Don't forget your constant. And then I'm going to rewrite this as 3 halves x squared plus c. When I take this one, I'm going to first rewrite this as x to the 1/3 power. So that's going to be our rule. Say we add 1 to the power, and we divide by our new power, and add our constant. And then dividing by a power is multiplying by the reciprocal. So I'm going to write that as 3/4 x to the 4/3 plus my constant. On here, now I have a full polynomial, so I'll first use the sum and difference rules. Integral of 3x squared dx minus the integral of 4x dx plus the integral of 7 dx. Don't forget your dx's on each one of those. It's so easy to do that. So then I'll use my constant multiple rule. 3 times the integral of x squared minus 4 times the integral of x plus the integral of 7. And then I can use my formulas. So 3 times x squared over 2 minus x cubed over 3. 4 times x squared over 2. Integral of 7 is 7x. And I have my constant. So I'll clean this up by saying 3 over 3 is just going to be x cubed. 2 over 4, or 4 over 2 is going to be 2. 2x squared plus 7x plus c. Again, once you get a hang of it, you probably are not going to do all of these steps on here. You will probably go straight from here to here when you're getting more comfortable with it. I encourage you to write this out to get this idea of why you're doing this. Now, if you notice on these three, we got more things going on. We will learn ways to deal with quotients. We will learn ways to do what do we do instead of a chain rule type of thing for integration. Whoops. Or what happens when we are a product rule here. But for these, you're going to simplify these down. Here you can divide or multiply out so that you can work with these. So give this a try. Multiply this out so it's a form so you can use those formulas you already know and do these. So give this a try. Unpause it and come back to me. So for this first one, I'm going to divide everything by the square root of x. So x divided by the square root of x is going to be 2 square roots of x. And this is going to be 5 divided by the square root of x. Actually, while I'm at it, not negative 1/2. That's a positive 1/2. So x to the 1 divided by x to the 1/2. I'm going to put it in exponential form because that's what my formulas are. So 5x to the negative 1/2. And so I'm going to rewrite this. This is 2 times the integral of x to the 1/2 minus 5 times the integral of x to the negative 1/2. I told you it's easy to drop those dx's. So the integral of 1/2 is going to be x to the, we add 1 to the power, and we divide it by our new power. Add 1 to the power, divide by our new power, add our constant. So that's going to be multiplied by 2/3, so 4/3 x to the 3/2 minus 2x to the 1/2 plus c. There's a lot of stuff on here, so I'll switch colors here. On this one, I would just multiply this out. The integral of 4x squared. 2 times 4 is 8, and we got 2 of those, so that's 16x. Negative 4 times negative 4 is 16 dx. So that's 4 times the integral of x squared minus 16 times the integral of x plus the integral of 16 is going to be 4x to the 3rd over 3 minus 16x squared over 2 plus 16x plus c. So that's going to end up being 4/3 x cubed minus 8x squared plus 16x plus c. Last one, I'm just going to take the constant out front. Let's start over here. 7 times the integral of x to the 1/4 times 5 minus x is 7 times the integral of 5x to the 1/4 minus x to the 5/4. Now, when I break this apart, remember I'm multiplying 7 times the whole integral. So I'm going to have 5 times the integral of x to the 1/4 minus the integral of x to the 5/4 dx is 7 times 5x to the 5/4 over 5/4 minus 5/4 plus 1 is going to be 9/4 over 9/4 plus c. So 5 times, or divided by 5/4 is just 4. But then we have at times 7, so I'm going to get 28 x to the 5/4. I'm going to take this 4/9 times x to the 9/4 times 7 is going to be 28/9 x to the 9/4. Now, I can take 7 times c, gives me 7c, but 7 times some unknown constant is still an unknown constant. So I don't have to worry about that. I can just leave that as c. 7 times c is c because c is any number. So, and I don't care what number it is. It's representing all of those different possibilities for that. So, to wrap this up, this was talking about general solutions. I want particular solutions. So, we're generally using, when we use this integration, we're using it to solve a problem. So we're looking for a specific situation. In order to find that particular solution, just one solution instead of an infinite number, we need an initial condition. We need to say, hey, this is what's going to identify which one I want. So an example here, my differential equation, because it has a derivative involved. F prime equals 10x minus 12x to the third, given that we need f of 3 to equal 2. This is my initial condition. So I start off finding my antiderivative. So I take the integral of 10x minus 12x cubed dx. So we'll break that apart. And again, we're stepping through bit by bit. So you see every step of the way to hopefully help you from getting lost, and then cover up the answer with this stupid power, this controls here. So we get the antiderivative, the general antiderivative is 5x squared minus 3x to the fourth plus c. That's your general solution. But I want a particular solution, so I'm going to say, well, this has to equal, if this is my function for f, I need it to equal 2 when x equals 3. So I plug in x equals 3, and I solve my solution for c, and I will get c is 200. So this can give me the particular solution I want. And so that's the one thing you need. When you solve a differential equation, you're going to get a general solution. To get you're going to get a function, an equation. To get a particular solution, you're going to need to have some initial condition. So, have at it.